Hi everybody, welcome back. Now this is going to be the 8th video from chemical kinetics, and this is going to be completely about solving problems. Now you will be given a few questions for self-practice as assignments. This is different from that. These are questions that look lengthy and they look scary as well when you read it in one go. But then if you sit and read it for 2 to 3 times, you can collect the concepts, put in all the formulas that you know, and we'll be able to crack it. Okay, so these are some model questions. Similar questions have been asked repeatedly, and I have put those questions in assignments. Okay, so let's try them. Read the question. If the initial concentration is 1 millimolar and concentration at different time intervals are given as follows. The order of the reaction is. Now, this is a type of question. Let me make this correction. Concentration at. Now, this is a question where T at 1, 2, 3, 4, 8, and 16 minutes are given. Corresponding concentrations are given. And we would like to find out what the order of the reaction is. What the order of the reaction is. Okay. Now, in none of the reaction, we can find certain relations, or the only way to solve this problem is trial and error. We can solve this problem by trial and error method. But what you have to understand is that because we don't know whether it is 0, 1, or 2, you will have to proceed with first putting the integrated rate equation of 0 order, solve it. Then put the equation of first order, solve it. And you have to find the case where the rate constant does not change. We'll be doing that. But what I want to suggest is that if you get such questions for the exam, you will mark it for review and then you will keep it at the end because it's lengthy and we don't want to waste time. We know the answer, we know the concept, but as it is lengthy, we'll mark it for review and then we'll be doing such questions at the end. Okay, our aim is to collect maximum number of marks in minimal time. So let's try. So they have given that the initial concentration of whatever the reactant is 1 millimolar, and at different time intervals they have given. Now let's try to put zero order reaction ka equation. This can be done through trial and error. So for zero order, for zero order reaction, what is the equation? Kt is equal to concentration of A naught minus A. Right? Initial concentration minus final concentration. So let's say that initially we take A at 1 minute. So we don't know the rate constant. This is equal to initial concentration is 1 millimolar minus the concentration that we are taking is at 1 minute, which is 0.83 divided by minute is 1. Okay. So the units are, this is millimolar and this is minute. So what do you get? 1 minus 0.83 divided by 1. So you will get 0.17 millimolar per minute as your rate constant. Now, even if you change the time, for example, you put it at 2 minutes, your rate constant should not change. Okay. So let's put it at 2 minutes. K is equal to initial concentration is 1 minus. Now you're taking the time at 2 minutes and the concentration that you have is 0.72. Correct. So 0.72 is your final concentration. This is in the units of millimolar. Divided by time is 2 minutes. Now 1 minus 0.72 by 2 is 0.14 millimolar per minute. Now this is not the same. Rate constants have changed when we took two different time intervals and that's not possible. Hence, it is not a zero order reaction. So we'll cancel that out. That is the only way we can do this. Okay. Now what will we do? We'll be taking the equation for first order reaction and we'll be doing trial and error. So let's try. Okay. For first order reaction, what is the integrated rate equation? Kt is equal to ln initial concentration by final concentration. Let's take two cases. You can take 2 or 3 to confirm. I'm just taking 2 because within that we'll be able to confirm. So case A is when you have T is equal to 1 minute and your final concentration is 0.83. This is taken from the table. So let's do that. K is equal to 1 divided by time is 1 minute ln of initial concentration is 1 millimolar divided by final concentration is 0.83 millimolar. Millimolar and millimolar gets cancelled. So this is unitless. Whatever you get over here is in units of per minute. And we know that for a first order reaction, the rate constant is going to be per time. And the answer that we get is 0.186. 0.186. Now we will put the same equation for another time. T is equal to 2, where the concentration finally is 0.72 millimolar. So let's try. K is equal to 1 by 2 minutes. Ln of initial concentration is 1, final concentration is 0.72. And when you solve this using your calculator, please do it, okay? 0.164 is what I'm getting per minute. Again, they're not the same. 0.18 and 0.16. They're not the same, so this is not a first order reaction. This is not a first order reaction. Okay, now case 3. You will put for zero order reaction. Not zero. We have already done zero for a second order reaction. For second order reaction. What is the equation? 1 by A minus 1 by A naught is equal to KT is our integrated rate equation. Again, we'll be doing two cases. Case A at 1 minute. At 1 minute. What is our case? Final concentration is 0.83 minus initial concentration is 1 is equal to K into time is 1 minute. Correct? So 1 by 0.83 minus 1. What I'm getting is equal to 0.204. What will be the unit? Here it is in millimolar. Here, okay, we'll do the unit in the next so that it's not confusing. For a second order reaction, it's always going to be millimolar per time. I'll show you how it is come. Now, next case is at T is equal to 2 minutes. Correct? You have 1 by, at 2 minutes, it's 0.72 minus initial concentration is the 1. So it's not going to change. Into 1 by time. What is time over here? Time over here is 2 minutes. And that is equal to the rate constant. So when you solve this, you will get the rate constant is equal to 0.194. Now they're very close. So if you have a confusion, you can try it once again. Another case. Another case. Let's say that at T is equal to, let's take another time, 4. T is equal to 4 minutes. Our final concentration is 0.56. So it is 1 by 0.56 minus 1 is equal to K into 4. You bring 4 to this side and solve, you will get K is equal to 0.196. You'll get K is equal to 0.196. Okay. No matter what time you take, the rate constant is not going to change. And here they're very closely related. And hence, the final answer is C. You need not worry about the units because they are all in a similar manner. You know what the rate constant unit of second order reaction is, right? Rate is equal to rate constant into concentration of A to the power 2. So rate constant will be equal to concentration per time as the unit of rate. So let's say that is in millimolar per minute, correct? And divided by concentration square, millimolar to the power 2. So finally, whatever you will be getting is per millimolar per time. Okay. Okay, that is per millimolar over here. Sorry, per millimolar over here. Why? Because concentration is at the bottom. Time is also at the bottom. So when it comes to the numerator, it becomes per millimolar per minute. Okay, so that's easy. So the correct answer to this question is option C, second order reaction. Now you can see that it was pretty lengthy. It was pretty lengthy, so you will be doing such questions at the end so that we don't run short of time. Okay. Next is a question which was asked in GATE. And the question is, for the reaction P plus Q plus R giving S, the experimental data for the measured initial rates is given below. So the concentration changes of P and the initial rates are given. We have to find the order with respect to P, Q, and R. We have done similar problems, but there is a twist at the end. Let's start doing. Now let's say that I want to find the order with respect to P. So if I want to find the order with respect to P, I have to find two experiments where my concentration of P is changing, but my concentration of Q is kept constant, concentration of R is kept constant, so that I can relate it to the rate. Correct? My concentration of P is changing, Q is constant, R is constant. So when my P is doubling, my rate is becoming, so this is 8 into 10 to the power minus 5, or I can write it as, this is same as 0.8 into 10 to the power minus 4. Both are the same. So 0.8 into 10 to the power minus 4 is becoming 3.2 into 10 to the power minus 4. Means it is becoming 4 times. So when you're doubling P, your rate is increasing 4 times. Means it is a second order reaction, right? We have done ample problems. So this is a second order reaction. So it's not option D. It's either A, B, or C. So the order with respect to P is equal to 2. Why? Because when you double the concentration, the rate is becoming 4 times. Now we need to find a relation where Q is changing, but P and R is not. For example, let's take this one. This one. So if you can see, our Q is changing from 0.5 to 2. 0.5 to 2, which is nearly 4 times. Which is 4 times. But your R is not changing. Your P is also not changing. These are kept constant. So when P and R are kept constant and Q is changing 4 times, what is happening to the rate? See what is happening to the rate? 3.2 into 10 to the power minus 4. If you want to write it in the terms of 10 to the power minus 4, this is going to be 12.8 into 10 to the power minus 4. So if you can see, your rates are increasing. 3.2 to 12.8 is 4 times. This is 4 times. Be careful with the powers, okay? You should know how to shuffle between -5, -4, -3, -5, etc. So when your concentration of Q is only changing 4 times, your rate is changing 4 times. Linear relationship, meaning it is first order kinetics. With respect to Q, it is first order. So it can be C, it can be B, but it's not A because over here it is given 2. Now there are 2 options left and you have to find the relation or the order with respect to R. Now the problem is, if you look at R, you cannot find a reaction where R is changing and P or Q are kept constant. You cannot find anything of that sort. R is still changing over here in 3 and 4, but P and Q are also changing. Okay, so in such cases, we'll have to take the ratio and find the order. So let's try. Let's give it a try. Okay, so let's say that I compare experiment 1 and experiment 4. Let's say I'm comparing experiment 1 and experiment 4. So I'll have to take all the values. So let's see, okay? Let's see how it goes. I'm just minimizing it. Okay. So what we'll have to do is the rate Yeah. So what we'll have to do is the rate of experiment 1 by the rate of experiment 2. This ratio is what we want. The rate constant of the reaction though won't change. So that will cancel out. So this is going to be equal to concentration of P for the experiment 1 is 0.2 to the power. What is the power of P? What is the order of P? It is second order reaction. So it will become to the power 2 into concentration of Q is 0.5 to the power 1. Concentration of R is 0.4 to the power, you don't know. Let's put it N. Divided by fourth experiment, your P concentration is 0.1 to the power 2. Their concentration of Q is 0.25 and your concentration of R is 1.6, whose power you don't know. Now this is what we have to solve. So let's check it once again. 0.2 to the power 2, 0.5 to the power 1, 0.4 to the power n, 0.1 to the power 2, 0.25. Yeah, okay. Now we'll consider the rates. What is the rate of the first experiment? It is 0.8 into 10 to the power minus 4 divided by 4 into 10 to the power minus 5. I can write it as 0.4 into 10 to the power minus 4. Both are the same. I have changed the powers. 4 into 10 to the power minus 5 is same as 0.4 into 10 to the power minus 4. Equal to. Now let's solve this. 0.2 to the power 2. Now be careful with the decimal places over here. Don't make mistakes. So this is going to be 0.04 into 0.5 into 0.4 to the power n, you don't know, divided by 0.01 into 0.25 into 1.6 to the power n. This is what we have got. Okay. Now, what is 0.8 divided by 0.4? So here 10 to the power 4 minus 4 gets cancelled and you get 2 over here. Okay. And you have 0.04 divided by 0.01. This becomes 4. Correct? And 0.5 divided by 0.25 is 2. So what do you have? You have 4 into 2 into 0.4 by 1.6. They have got a common power raised to n. Now 2 and 2 will get cancelled. 4 will come to this side. 1 by 4 is equal to 1 by 4. 0.4 by 1.6 is 1 by 4 to the power n. Now this is very easy. For what power of n will the LHS be equal to 1.4? Sorry, 1 by 4 when you have n is equal to 1. Which means the order with respect to R is 1. That is the only tricky part. So it's not B, it is C. It's a very good question. It's option C. So this is the way you do it. You can take any experiments, okay? You can take either 1 or 4, 2 or 4, 3 or 4. Any experiments where the concentration of R is changing can be taken. Okay? All right. Next question. The decomposition of gaseous acetaldehyde at temperature given in Kelvin follows second order kinetics. Second order kinetics. The half-life of this reaction is 400 seconds when the initial pressure is 250 torr. What will be the rate constant in per torr per second and the half-life in seconds respectively if the initial pressure of acetaldehyde is 200 torr? It's a very easy question. They have asked two parameters, that's all. Already they have given that it is a second order kinetics. Now they have given, instead of a solution where the concentrations are given in molarity, here they have given gaseous reactants where instead of molarity, you will be given changes in pressures. You will be given changes in pressures. Okay. So first of all, they have given that initial T half 1 was 400 seconds when your initial pressure, so this is acetaldehyde, let's say P naught 1 was 250 torr. Now they are asking if the initial pressure is changed to 200 torr, what would your new T half be? This is the question. Now we already know the relation between T halves and the initial concentration. What is that? T half 1 by T half 2 is equal to the initial pressure for the second experiment divided by the initial pressure for the first experiment, the whole raised to n minus 1. They have already given that it is a second order reaction. Correct? They have already given that it is a second order reaction. So let's try the initial one. Let's say it's 400 seconds divided by, you don't know what the second half-life is equal to initial pressure for the second experiment, which is 200 torr, that will get cancelled, divided by 250 torr raised to 2 minus 1 it is. That's it. Now we need to rearrange and solve. That's it. So you will get 400. Let me calculate. 400 into 250 divided by 200 it is. So I'm getting 500. 500 seconds. 500 seconds. So it's not option C or B. It's either A or D. It's either A or D. Now, what is the next parameter they have asked? They have asked us to find the rate constant. That is also very easy. You know that for a second order reaction, T half is equal to 1 by initial concentration into rate constant. So K is equal to 1 by, let's put the first experiments ka values. 400 seconds into the initial pressure was 250 torr. That's it. We need to solve this. So we will get 1 divided by 400 into 250. That is going to be 10 to the power minus 5 per second per torr. Option D. Option D is the correct answer. This was asked in June 2011. Asked in June 2011. All right. Next, please mark it as important. Just a second, please. Okay. Sorry for the delay. So now, let's solve this. Please mark this question as important. So the question is, the carbon-14 activity. So when you just look at the first word, you have to understand that this is from radioactivity. Okay. So the carbon-14 activity of an old wood sample is found to be 14.2 disintegrations per minute per gram, which is of an old one. Calculate the age of the old wood sample. If for a fresh wood sample, the carbon-14 activity is 15.3 disintegrations per minute per gram. Also, it is given that T half of carbon-14 is 5730 years. Just a second, please. Yeah, okay. So it's a very easy question. It looks tricky, but it's very easy. So see, you have been given with a question where the old wood sample has got some integration, disintegrations, and the fresh has got a different integration. Now, integration is the rate at which the decay is happening. So initially, this is the initial one. Initially, it is 15.3. Finally, at this stage, it is 14.2. They have given the T half. You have to find the time at which this initial A naught becomes A. It's very easy. So first of all, we'll find the rate constant. Let's try. How to find? We know that T half is equal to 0.693 by K. Okay. Now from this, we can calculate K, which is 0.693 divided by 5730 years, which is equal to, once you calculate this, you will get it as equal to 0.001209 per year. This is your rate constant. Now what is given? At T is equal to 0, your initial concentration, instead of concentration, they have given it in terms of disintegrations. That is fine. It was 15.3 whatever units, they are the same. And at some time t, the final concentration has become 14.2 disintegrations per minute per gram. You know K, you have the initial concentration, you have the final, you have to find T, you have to understand that carbon-14 decay is a radioactive process and that is going to follow first order kinetics, that's all. So what is the equation? T is equal to 1 by K ln of initial concentration divided by final. That's it. So 1 by 0.000129 per year ln of, initially it was 15.3, finally it was 14.2. We need to solve this. That's all. I have already solved it. Please try it using your scientific calculator and we'll get it approximately as equal to 617 years. 617 years. Okay. Next question. Again, a beautiful question. Looking at the question, we might think that we won't be able to do, but then it's very easy. So let's read. A bacterial colony grows most commonly by cell division. The change in the population due to the cell division in an actively growing colony is dn is equal to lambda n dt. The population of bacterial colony at any time t is. So what is given? It is given that the changes in the population, the small changes, read the question very well. The changes in the population dn is given as lambda g n dt. And what do they want? They want the population, which is n. Very easy. Small changes are given. They need n. We have already done this many times. We need to integrate it. That's all. Try it on your own before you see the solution now. So I will rearrange this. dn by n is equal to lambda dt. Integrating it from t is equal to 0 to t is equal to t, where initially it is n0 and finally it is going to be n, of course, right? So what is dn by n? Ln n, put the limits, lambda gt, put the limits. You're already familiar with such integrations. So it's going to be ln n minus ln n0 is equal to lambda into t. Or ln n by n naught is equal to lambda into t. So if I take anti-ln on both sides, n by n0 is equal to lambda into t. Sorry, when you take anti-ln on both sides, this becomes e to the power minus lambda into t. And I can take n0 to the other side. My final answer is going to be n is equal to n0 e to the power minus lambda into t, option B. That's all. Easy. Understand that e to the power x can also be written as exponential x. This is also, they are the same. They are the same. Okay. Next question. A similar question, which we have already done. You can try it on your own now. In a sample of charcoal, the remaining fraction, pay attention, it's not the remaining amount, it is the remaining fraction which makes this question very beautiful. Students will make mistake over here. It's not remaining amount. Understand the difference. What is remaining amount? Remaining amount, whatever is left. For example, if the initial concentration is A naught, Then the final concentration is the remaining amount, which is A. Okay. Here they have given the remaining fraction. Fraction means it is always relative. Understand that. Very important. Remaining fraction. Fraction means it is A, which is the final amount, to the initial amount. It's the remaining fraction. Okay. If there are 10 balls in a box, I have taken 2. I have taken 2 out of 10 fraction of the balls, 2 by 10. So it is a fraction. This is important. So this fraction is what is given to you as 2 into 10 to the power minus 2. Very important. You have to read the question well. It's not remaining amount, it is remaining fraction. Now it's easy. You have to find its age t if t half is given. Again, it is C14. You know it is a first order reaction. Now you can do. So with T half, we can find K. K is 0.693 by T half. Already we have done this 2 questions ago. 0.693 by T half. 5730 is going to give us 0.0001209 per year. This is the rate constant. Now we need to find time, for which you will be using the integrated rate equation. Kt is equal to ln A naught by A. Understand, here we have A by A naught. And in the equation we have A naught by A. So we will write it as Kt is equal to ln of, it is the ulta, we'll take the reciprocal, 1 by 2 into 10 to the power minus 2. Okay. So time is equal to 1 by 0.0001209 per year, ln of 1 by 2 into 10 to the power minus 2. You can solve this. Try. You will get approximately 3.2 into 10 to the power 4 years. Option A. 3.2 into 10 to the power 4. Oh. It's a good question. You have to read the question well. Next, the beta activity of 0.9 gram of carbon from the wood of a present day tree is 0.25 BQ. Okay, now just understand that your activity could be given in disintegrations per minute per gram, or this is another unit BQ, which you will be learning in depth in the nuclear chemistry topics. Okay, so you have to understand that activity, the present day is 0.25. Now, if the activity of the carbon is isolated from a wood of an ancient artifact, means it has become old. Now, of course, this is 0.25 is greater than 0.9, 0.19. So this is going to be your initial value. This is going to be your final value. Under the same conditions, you have to find the age. T in years, T half is given. Same question, different language, that's all. You know the pattern. How is it done? You will find K first, 0.693 by T half. Now, this is the third time we are doing this, which is equal to 0.0001209 per year. Okay. Now, you will use the integrated rate equation. T is equal to 1 by 0.0001209 ln of initial value of the disintegration. Initially, it was 0.25. Finally, it is 0.19. That's it. Okay, so you can solve this, and the nearest answer is going to be 2268 years, option C, the nearest one. 2268. Okay. Next question was asked in CSIR. Again, why I had put this question is because now this is actually related to polymer. I had already mentioned that when you learn chemical kinetics, the applications of chemical kinetics comes in certain other chapters like photochemistry, polymer chemistry, and surface chemistry. So this is actually a question from polymer, but then you need not know anything about polymers to solve this problem. So let's start. The fraction of groups condensed at time t at any stepwise condensation polymerization following second order kinetics is. It's very easy. You try to pause the video and do it on your own. I have highlighted the two main important words in the question, which is the only things that you need to solve the problem. So what is given? There is some monomer which condenses to form the polymer. There's a condensation reaction. So initially, let's say it was A and 0. Finally, some amount of the monomer will condense to form the polymer. They don't want the amount of the polymer formed. They don't want the value of X. They want the fraction of groups condensed. So that is very important. Fraction. Fraction means it is always the amount of polymer formed divided by the initial concentration. So this is the value that you have to get. That's all. Now you can do it on your own. It's a second order reaction, right? So for the second order reaction, what is the integrated rate equation? 1 by final concentration minus 1 by initial concentration is equal to K into T. Correct? Now our final concentration is, so I'll change the final concentration as A minus X and the initial concentration as A. Now I'll rearrange this. So if I take the LCM, this is going to be A minus A plus X divided by A minus X into A is equal to KT. A and A gets cancelled. This is X by A square minus AX is equal to KT. We need the expression for X, okay? So let's rearrange. X is equal to A square KT minus AX KT. I'll bring X terms to the side. So it becomes X into 1 plus AKT is equal to A square KT. From this, X is equal to A square KT by 1 plus AKT. Now look at the options. This option is there. A square KT by 1 plus AKT, but this is not the answer. They have not asked for the amount of the polymer formed. They have asked for the fraction, which means you have to divide it. Fraction means you will divide A square KT by 1 plus AKT divided by A. Okay, so it is AKT by 1 plus AKT. AKT by 1 plus AKT, option D. Option D. So say you know the concept, you know the equation. It's just about rearranging and reading the question really well. Okay. Last question. It's an easy one. How does the time required for a first order reaction to go to 99% completion relate to half-life? So see what the question is. Listen to what the question is. They have asked 99% completion. So at 99% completion, let's say that your initial concentration was 100 your final concentration would be 1 because 99% is complete and you have only 1% left. Correct? So let's say that this is T99. Now we have to relate it to T50 percentage. Already you know that at T50 percentage, let's say your initial concentration is 100, your final concentration is going to be 50. You already know that. So you need to find the relation between T99 and T50. Now already it's given that it is a first order reaction. And you know that for a first order reaction, T half is 0.693 by K. You're aware of this. 0.693 by K. So we need to find the relation. You can find the ratio, anything works. So let's try. So for T99 percentage, the integrated rate equation will be Kt times 99 percentage is equal to ln of initial concentration by ln of final concentration. Correct? Now for 50 percentage, it is equal to ln of 100 divided by 50. So let's say this is 1, this is 2. So T99 percentage by T50 percentage is going to be, my rate constant of the reaction is not going to change if I divide 1 divided by 2. So K and K gets cancelled. So you have ln 100 by 99. So let's see what that is. 100 divided by 99. Ln, let me calculate please. 100 divided by 99. Okay. So I have got it as 0.01005033 divided by ln 100 by 50 is ln 2, correct? And we know that the value of ln 2 is 0.6931478. So I'm taking these many digits because it is in natural log. And the more you approximate, the more error to create. So let's try to find the value. 0.01005033 divided by 0.6931478. There's some problem. Just a second, please. We'll do it the other way around. So this ratio, what I'm getting is 0.0144. What if we do the other way around? 0.6931478 divided by 0.0100503. I'm making some mistake. Just a second, please. Is there a T99 by T50? So I want to write how does time required for a first order reaction to go to T99 completion relate to T half? Relate to T half. Okay. Yeah, so what is wrong? 100 divided by 99. Just a second, please. Oh, I got it. What I have been doing is I have to put the amount of A left. Okay, that is what I'm missing out. So this is 1. Okay, that is the problem. Okay, this is 1. Sorry. I'm so sorry. I'm so sorry. That is the problem. Okay, I got it. So it is ln 100 by 1. So that is ln 100, which is 4.605. That is the mistake that I made. Now let me try. 4.605 divided by 0.693 is giving me 6.6, which means T 99 percentage is equal to 6.6 of T 50%. Okay, that is where I made the mistake. I'm so sorry. Okay. Yeah. So it's going to be option. Okay, I need to be more accurate. No. 6.2 and 6.6 are correct. Our correct answer is 6.6, option B. Okay. All right. So with that, we have completed all the questions. I hope you learned new models. And with that, we'll be ending and we'll be moving to the next part. Okay. So thank you. A nice day.